Hello everyone, welcome back to another lesson in integral calculus. And in this video, we will learn to calculate areas using integration. Now, in my first video, I said that the function or the use of integration is to calculate areas under a curve, okay, or an area that is being bounded by two or more curves. And this area can be calculated using the basic formula that we have encountered in our analytic geometry, okay, since this area again is bounded by a curve. Now, like for example, this region here that is being bounded by this line and this curve here, and this curve has an equation of y is equal to function of x. Now, we know that we cannot calculate this area or this region here by simply using the geometry formula such as the length times the width, okay, or the area of a rectangle, the area of a triangle, and so on. So the best way to calculate this area is by integration, and we know that our area here is bounded or is limited from A to B, since this is the area that we are calculating, that is from the region or that is has a limit from A to B. To calculate this area, we need to divide this region into a several or an infinitely small rectangle. Let this be a very small rectangle having a width here. Let's say that is our length, and this one is our width. Since this rectangle is very small, so we set our width here, that is our change in x or the derivative of x, and our L here, that is the height, okay? And if we plot this point here at any point in our curve, we have y, or that's the coordinates of y. So therefore, our L here is simply equal to the y coordinate of our curve, okay? And our y here varies with the change in its x coordinate, since we know that our y is a function of x. So as our x or x coordinate is changing, our y is changing at the same time. So therefore, the height of the rectangle changes in every location from A to B. So we have different y or the height from A to B. So therefore, we can see that our L here, or the length of our rectangle, is equal to the function of x, since this is the value of our y. So therefore, our area here is equal to the area of the rectangle is length times the width, correct? And since we have very small rectangle, we divide this into very small rectangle. Then we sum up the area of this rectangle to approximate the area of this entire region. Okay? So therefore, we have the integration that is from, the limit is from A to B. Okay? And our L here, that is our function of x, correct? Since that is our height. Since our height again is changing with respect to the change of its x coordinate or its location. So therefore, we have our length, that is the function of x, and the width here, that is a very small width or infinitely small width here. So therefore, this is derivative of x. So this is the general form of our area. So we sum up the area of the rectangular strips from A to B. That is this one again. This is the height. It's the function of x. And this is the width. That is the derivative of x. So depending on the orientation of the strip, of course, there are some instances that we need to have, like for example, a horizontal strip. So like this one. So we have our width here, that is our dy, and our height, that is the x. Okay, so our equation or the general form for the integration changes depending on the orientation of our strip. It would be either vertical strip or horizontal strip. Now in calculating area, it is very important that we know the basic in analytic geometry, especially in plotting curves in our Cartesian coordinate system. Okay, so that's the most important thing that you need to know or you need to have before proceeding to this topic. One of the curve that most probably we will be encountering all throughout this lesson is parabolic curve. Now we know that the general equation of the parabolic curve from our analytic geometry is y minus k squared is equal to, we have plus minus 4ax minus h, where in our h and k here, that is the coordinates of our vertex. Or when we say vertex, that is the maximum point or the minimum point of our parabola. Okay, so therefore, if we have a positive equation here, then we have rightward. So, for example, in this case, this is the vertex, and the vertex has a coordinate of hk, correct? And this is in rightward, so therefore, it is a positive parabolic equation. Now, if it is leftward, thus it has a negative parabolic equation. That's the reason why I put positive or negative here depending on the orientation of our parabolic curve. Now, k here, that is the y coordinates of our vertex, and h here, that is the x coordinate of our vertex. Now, for this general equation here, wherein we have our x minus h here, that is being squared, is equal to plus minus 4a y minus k. So it is different. So we have our x here that is in the second degree since it is being raised to the 2. So therefore, if we have upward, like for example this one, this is the vertex, so thus it has a coordinate of hk. So since it is upward, therefore that is positive. Okay, so therefore that is plus 4a y minus k. If it is acting downward, or its curvature open downward, so therefore that is negative parabolic curve. So therefore it is negative 4a y minus k. Okay, so our goal here before we can plot our parabolic curve is to determine, of course, where is the location of the vertex, or what is the coordinate of the vertex. That's the easiest way in calculating the area. So you need to know those basic knowledge that we encountered in our geometry. If we have our parabolic curve that is the which is our vertex is at the origin, okay, so therefore our h and k here is equal to 0 since our vertex coordinate is 0, 0, or is at the origin. So in that case, if we have this curve here and our vertex is at this point, that is the origin, so we have our coordinate that is y squared is equal to 4ax. So this is the general formula. And this is positive since it is acting, or that is opened rightward. Now for this curve here, we have y squared is equal to negative 4ax. Now, for this one, we still have our coordinates at the origin, and it is opening upward. So, therefore, we have x squared is equal to 4ay, that is positive. Now, for this curve that is opening downward, that is, we have x squared is equal to negative 4ay. So, these are the general equations of a parabola when our vertex is at the origin. Okay, again, if our vertex is not the origin, then we need to use this general form here, where our y, this besides our, this is the y coordinate and this is the x coordinate of the vertex. And now I have here our first example. We are asked to calculate the area of the region bounded by the curve y is equal to 4 minus x squared and the x-axis. So we have an equation of the parabolic curve here. This is parabolic since our equation here is raised to the 2, or that is in the second order. So therefore, we need to plot this equation in our Cartesian coordinate system. That's the best track that we need to follow in order to come up with the correct area. If you're an expert, then you can proceed or you can go directly with the integration. But I guess in order to understand it better, so we need to plot first this equation here. Now, however, what we need to do is to compute for the vertex of the parabolic curve first. Now, we have the equation, that is y is equal to 4 minus x squared. Okay, now it resembles with the general form or general parabolic equation, that is x minus h squared is equal to 4a y minus k, in which you can rearrange this equation similar to this form. Then we have x squared is equal to 4 minus y. If we try to follow this form, then we could have x minus 0 squared is equal to, now our y here is in the first term, then we can say that it is y, okay, negative y plus 4, correct? That is x minus 0 squared. This is x minus 0 squared, since if we evaluate this term here, then we would come back at x squared, correct? Since this is 0. And we know that our y here is positive, so therefore we factor out negative sign, then we have here negative y minus 4. Since if you distribute negative inside the parenthesis, then we would come back to this form here. So therefore, we could say that our h here is equal to 0, correct? And our k here, that is equal to 4. Since this is y minus 4 and this y minus k, our k here is 4. So this is the coordinate of our parabolic curve. Now we know that it's a negative from the formula. If this negative here, so we have a parabolic curve that is opening downward. Okay, just like this one. Since this is a negative equation and we have our x here that is raised to the 2. Now, we have another way in computing for the vertex. We just need to apply the concept of maxima and minima from differential calculus, that we know at the maximum point, like for example, if this is our curve, at this point, that is the maximum point, correct? And at that maximum point, the slope of our tangent line is always equal to 0, correct? At the maximum point, the slope of our tangent line or the slope of that point is equal to 0. So therefore, if we derive the equation of this curve, our first derivative, which is just equal to the slope, is equal to 0. Okay? So that's how you are going to locate for the maximum or the minimum point. So the same as with the minimum point, at this point here, our first derivative is always equal to 0. So we can derive this equation, then we could have a y prime is equal to negative 2x, correct? Now, at y prime is equal to 0, so we have our x here that is equal to 0 as well. Okay, so therefore, this is the coordinate at the maximum point. Now, for the y coordinate, we just need to substitute the value of x in our original equation. That is, we have y is equal to 4 minus x squared, and our y here is equal to 4 minus our x is 0 squared, so therefore we have y is equal to 4. So this is the y coordinate at the maximum point. So therefore, we have our vertex coordinate, which is at 0, 4. So this is the coordinate of our vertex. Now we have computed already the vertex, then we can now go to the plotting of this equation here in our Cartesian coordinate system. Okay, so let's try to plot this equation. X squared is equal to negative y minus 4. Again, we know that this is a parabolic that is opening downward, since we have negative here, or that is a negative equation. So, and we have our vertex here, which is 0 and 4. this is the coordinates 0, 4. So let's plot it first in our Cartesian coordinate system. We have our vertex here at this point, which is 0, 4. So this one is 0, 4. Again, this is opening downward. Then we have our parabolic curve, which is this one. Now, upon looking at the Cartesian coordinate system, there is a point of intersection between our curve and the x-axis, and this point is this one, okay, and this point here. So how are we going to determine this point of intersection? We will be needing it so that we can identify, or we have the data for the limit of our area, which is at this point up to this point here. Now, how are we going to determine this point of intersection? We just need to know that our y here is equal to 0. We don't have y coordinate at this point, correct? And as well as at this point, we do not have y coordinate. So therefore, our y is equal to 0. So going back to our general equation, then we can set y here is equal to 0, is equal to 4 minus x squared. This is our new. So therefore, we can further simplify this equation as x squared is equal to 4 and x equal to square root of 4. And we have two roots to this one. We have positive root and negative root. So therefore, that's x equal to positive and negative 2. So therefore, when our y is equal to 0, we have two values of x. That is, x is equal to positive 2. And the other one is x is equal to negative 2. So therefore, the point of intersection where our y coordinate is 0, we have here that is 0, negative 2, correct? Since this is on the left side of our Cartesian, that is negative 2. And at this point, at the right, we have here 0 and positive 2. So that is the point of intersection of our x-axis and the parabolic curve, which has a equation y is equal to 4 minus x squared. Okay, so we have already drawn the parabolic curve in our Cartesian coordinate system. So we can now proceed to the computation of the area. Now take note, our problem here asks for the region that is bounded by 4 minus x squared and the x-axis. So therefore, we have this entire area to compute. So we need to calculate the area that is bounded by this curve and the x-axis. So this shaded region, okay, so we are going to calculate the area of the shaded region. So again, we need to draw a vertical strip. Okay, let's say our vertical strip, we have, and this vertical strip here, let's say the height y and the width that is in derivative of x, since our vertical strip is infinitely thin or infinitely small. Okay, so therefore we set as the width here, that is the derivative of x. So from the area, we have the area is equal to the integration of, that is y dx. So we have again, this is resembles to the length times the width area of our rectangle. So we have our area here, which is our y. We know that is the function of x dx. And in this case, our limit, since our area is from this point up to this point, okay, so therefore we have our limit from negative 2 to 2. From negative 2 to 2, so this is a definite integral. And our derivative of x here varies from negative 2 to 2. Now, our function of x here, and that is our y, is equal to 4 minus x squared, correct? So therefore, we substitute function of x here as 4 minus x squared. 4 minus x squared dx. Okay? So we have our area Then we integrate. We have 4x minus x cubed over 3. Then we have limit from negative 2 to 2. So our area is equal to 32 over 3, or which is 10.667 square units. So this is the area of this region from negative 2 to 2. Now you can check it by using the formula from geometry. We have the area of the parabolic bounded by a line that is equal to 2/3 base times the height, where our base here is this length, and this length here is 4, since we have 2, and this one is 2, so therefore we have 4. And the height is from the vertex to the origin, which is also 4. So we have the area, which is equal to 32 over 3 square. So therefore, the area, or this is our final answer. And that ends our first example, and we will have another example in my next video. So for the part 2 of this discussion, just click the link in the description.